Now we see the characteristics of polymers. Most of the polymers are having low density, low coefficient of friction, good corrosion resistance. That's a very, very important point. A good mold ability. That's why for different shapes we can mold it, reshape it. Poor tensile strength, low mechanical properties, poor temperature resistance, can be produced transparent or different colors. So for these reasons, for poor tensile strength, low mechanical properties, and a poor temperature resistance, so people will go for reinforced plastics or FRP, CRP, GRP. This reinforcement will enhance these properties. Applications of polymers. These polymers plays a major role in medicine. And consumer science, in industries, in sports. In medicine, many biomaterials, especially heart wall replacements and blood vessels, are made up of polymers like Degron and Teflon, etc. In consumer science, plastic containers of all shapes and size are lightweight and economically less expensive than more traditional containers. In industries, automobile parts, pipes, tanks, packing materials, adhesives are all polymer applications used in industrial market. In sports category, the playground equipments, golf clubs, swimming pools, and the protective helmets are produced from these polymer materials. These are all the list of polymers and its characteristics, linkage, and its applications. Out of this, I will just read out the important polymers that is covered in this topic. So polyvinyl alcohol, that is CH2CHOH. This polymer used in as fibers, adhesives, and textiles industry. And polythenes are having two classifications: low density polyethylene, high density polyethylene. The molecular formula is CH2 N times. Coatings, containers, films, packaging, housewares. In these fields, these are very much useful. In polystyrene, CH2CH6H5. It is useful. It's similar to polythene. Besides this packing materials, the packing materials that forms is nothing but polystyrene materials. Polypropylene PP we discussed few slides back. This will be in three forms: isotactic form, symbiotic form, adactic form. And the formula is CH2CH CH3. So one difference from this and polythene is that from polythene, one hydrogen will be replaced by one methyl group. So that polymer is called as polypropylene. It is used in the preparation of carpets, bottles, wrap films. And PMMA, that is polymethyl methacrylate. It is a polymer prepared from methyl methacrylate The formula is CH2, CH3, COO, CH3 n times. It is used for the transparent windows, plexiglasses, plus and Teflon or polytetrafluoroethylene is important polymer. This is that's particle formula is CF2 n times. This has another name or commercial name, Teflon. In kitchen applications, this Teflon plays a major role. Non-stick tawa, we used to say, for making dosa and all. There, the inner coated material is nothing but Teflon. And PVC, what is PVC? Polyvinyl chloride. The molecular formula is CH2CHCl n times. PVC, we use it as a insulating materials for electric wires, insulating pipes, plastic seats in the indoor stadiums. Polymer recycling codes. So you can see in the polymer back this symbol with the numbering 1 to 7 and the code PETE means it is a polyethylene terephthalate. It is used for the preparation of soda bottles and clothing. Number 2 is high density polyethylene. It is used for making toys and so milk, the plastics, double box, water jugs, nothing but high density polyethylene. And that code 5 means it is a polyvinyl chloride. Number 3 is used in the preparation of pipes, floorings and all. LDPE means low density polyethylene used for carrying the vegetables, the plastic bags, squeeze bottles. And polypropylene is nothing but the abbreviation is PP. Number 5. It is used to prepare the containers that can withstand high temperature in microwave heatings and all. This material will be used. And polystyrene, thermocols is nothing but polystyrene. Besides disposable cups, fast food containers, insulating foam, cassette tap boxes are all nothing but polystyrene. Here you can see the number code. So 1 to 6 that indicates the different polymers. Our next topic is difference between addition polymers and condensation polymers. First, I will address about the addition polymers, its synthesis, properties, and then its applications. Then I will discuss about the condensation polymers. Then we'll go for the difference. Addition polymers means polymers prepared by addition reactions or addition polymerization reactions. These are all the examples for this. Examples of the monomers under this category: ethene, styrene, cyanoethene, vinyl alcohol. These are all examples for the monomers that is used for the preparation of addition polymers. So when we use ethene, we get the polymer by addition mechanism, that is polyethylene or polyethylene. When we use styrene, we get the polymer, that is polystyrene. When we use cyanoethene, we get the polymer, that is Orlon. When we use vinyl alcohol, we get the polymer, that is polyvinyl alcohol. It is a polar polymer, water-soluble polymer. On the other hand, for condensation polymers, we discussed already, two or more than two monomers will react. The monomer should have a functional groups. Okay. For example, you see 1,6 hexane diamine. Here the amine is the functional group. There are two amines. Okay, and another monomer is adipolyl chloride, where here the functional group is COCl, 2COCl and 2 amines. These both will combine during the reaction. Just if you heat it, you will get the compound. What happens is that from the amine group one hydrogen, and from that adipolyl compound one chlorine. So HCl will be eliminated. We get the nylon. 6,6. So which molecule will be the side product here? So hydrochloric acid. So I will write here as minus HCl, isn't it? So suppose if you need to go for the nylon 6,6 for higher applications, or if you want to increase the hardness or stiffness or tension strength, generally what people will do, they replace this methylene group with phenyl group. If we replace this methylene with phenyl group, what happens? The hardness, the strength, the tensile strength, the stiffness will be increased. So we have to convert, we have to go for aromatic instead of aliphatic. So the phenyl means C6H5, it's aromatic group. Okay, so what will be the monomer for this high-end polymers? Instead of hexane diamine, you have to go for phenylene diamine. Here you put phenylene. Here there are two amines are there. You end up with a product. Or here also you can go for a aromatic group, phenyl group. If you go for aromatic group, phenyl group, this compound will be called as allyl chloride. Instead of Cl, if there is OH, it is phthalic acid. So if you, based on your applications mainly, we can modify the monomers and we can get the desired product. So the mechanism of addition polymerization reactions, there are three steps already we discussed 10-15 slides back. There are three steps: initiation steps, propagation steps, and termination steps. In the initiation steps, what happens is that the peroxide will undergo the cleavage, homolytic cleavage. It ends up with alkyl radical. Okay, suppose if this is the peroxide linkage, we have the acetyl group here or benzyl group here, no problem. This bond will cleave at the center, that is homolytic cleavage. We get two times this molecule here on the same side, here the identical molecule, here the identical group. So two times this molecule you get. So this on dissociation you end up with two times alkyl radical. It may be methyl, it may be two times, it may be methyl, it may be phenyl. Okay. So this methyl radical will go and attack this carbon. When it will attack, when this double bond dissociates into two radical species, one radical will sit over here, another will sit over here. Now you have your radical here, you have your radical here, this will go and combine here. Is that? Yes, these two radicals will make a covalent bond. Z will go and here, bond with here. So we get Z, covalent bond, this carbon. But this radical is free. Yes. So this step is called as initiation. What is initiation? The reaction is getting initiated. That means what? The catalyst, that is peroxides, will give us an alkyl radical or aryl radical. That radical will go and attack the monomer. We get a monomeric species attached with the initiators that has a end terminal radical species. That radical species will react with another monomer. How means this bond will be cleaved, and you will get one radical here, one radical here. This radical will make a bond with this carbon. Understand? So it will be extended. The ring chain will be extended, and since it has two radicals, one is here, one is here, this will make a bond with this carbon, but this radical will be active for further reaction, isn't it? So like that, if you put n number of monomers, so one by one, step by step, each monomer will be added. So that step is called as propagation step. What is this name? A propagation means what? It is the chain is keep on extending. Okay, and then so these reactions will be repeated based on your demands. Suppose if you go with a high density polyethylene with, let us say, 50,000 units, you add 50,000 units, Each one will go and add to the intermediates, and after the reaction is completed, somehow we have to stop the reaction. That reaction is called as termination reactions. So what will be termination? The end radical species is supposed to be getting terminated. How do you do that? So you can do that by two ways. One way, uh, suppose this hydrogen will be eliminated as hydrogen radical, and this carbon will have a suppose this hydrogen, let us say, okay, this hydrogen will go as H radical, and this carbon will get a radical species. How the carbon will get radical species? Because this bond has two electrons. When this bond is cleaving, one electron will reside over the hydrogen, other electron will reside over the carbon, and hydrogen will go as a byproduct as hydrogen radical. This carbon will have a radical, and this carbon will have a radical. Two adjacent carbon has two radical species will make a bond. So you end up with a unsaturated double bonded polymer. This is so intramolecular termination reactions. Okay, suppose if you another possibility is that that excess of methyl that radical is there, no? That radical also will have a chance to coordinate to this carbon, and it will be CH3. The reaction will be quenched. In some cases, if you treat with a base, let us say ammonia, ammonia will dissociate as hydrogen radical, NH2 radical. That hydrogen radical will go and bind with carbon radical. The terminal active radical species will be reneutralized or quenched. This is addition polymerization reaction mechanism. Condensation is very simple. Just two monomers, different monomers will react with sometimes water elimination. Sometimes methanol elimination, we get the product. This is a famous polymer, that is the melamine formaldehyde polymer. You start with melamine. What is melamine? It is a aromatic trinitrogen, tricarbon systems. There are three nitrogens in the aromatic ring, and there are three carbons. It's like in benzene, if you replace three carbon with three nitrogens and three amine groups attached to the carbon of that ring, one amine is attached here, another amine is attached here, another amine is attached here. This is called as melamine. When this melamine reacts with formaldehyde, we get the melamine formaldehyde. This is the reaction. What is the reaction? The NH2, very simple. You remove one hydrogen, NH, put it here, CH2, O, this hydrogen will come here, so CH2OH, that's it. CNH, CH2OH. Okay, like that, at three sides, there is a formation of a carbonyl derivatives by reacting with the amine functional groups. Okay, NaCH2OH. And further reactions, further addition of the alcohols, okay, will lead to the further condensation. We end up with the polymer that is called as melamine formaldehyde or butylated melamine formaldehyde. Okay, this is a known polymer for condensation reactions. And thermostatic polymer. For thermoplastics, you write the preparation of the ethylene to polyethylene and styrene to polystyrene and chloride to polyvinyl chloride. All are examples for thermoplastics polymers. Now, thermosetting polymers, one thing you should remember, thermosetting means it's very hard, very rigid, high tensile strength, good mechanical properties polymers, which is needed for different applications. How do you prepare that? The example I given here is a bakelite. What is bakelite? Bakelite is nothing but phenol formaldehyde resin. Phenol formaldehyde resin. That's another name. Okay, that means you need to use two monomers. You should remember one thing. This thermosetting plastics or polymers are coming under the category of condensation polymers, where two or more than two monomers will react. This is formaldehyde, this is phenol. So the net product we call it as a phenol formaldehyde resin or bacrylate resin. Okay. So here, what is the chemistry? Chemistry is very simple. Just imagine you have hydrogen here, you have hydrogen here. Okay, and you have hydrogen here. What happens? Same like melamine formaldehyde. This hydrogen will react with the formaldehyde. What is formaldehyde? Formaldehyde is like H, C, double bond O, H. So you remove the hydrogen, put it to the OH. It will be one bond at this side, CH2OH. That's what we see here. One bond, CH2OH. Similarly, if that reaction takes place at the ortho sides, this is para one. Okay, and here we get this CH2OH group at the ortho position. Here we get CH2OH group at the ortho position. Understand? So when you heat further, water will be eliminated. You end up with the intermediates, that is double bond CH2, and this you treat with further phenols. Okay, further phenols, there is a uh, compound, that is phenol formaldehyde resins. If you have another aldehyde, water will be eliminated. Here the chain will be extended like this. Chain will be extended like this. Chain will be extended like this. Here also there is a possibility of ortho position to this OH. Okay, ortho position to the OH. So like that chain will extend. Finally, you end up with a 3D network polymer. It has another name, that is bacrylate. What is bacrylate? A cross-linked polymer made up of two different monomers. What are the monomers? One is phenol, other one is formaldehyde. So we call it as a phenol formaldehyde resin. Solution polymerization, here it is nothing but, so there are some limitations in the radical polymerization and the condensation polymerization. To overcome that, so we can do the reactions in solutions. Okay, so the limitations of the bulk polymerization can be eliminated with the use of this solution polymerization reactions. So here what we do, along with the initiators, we dissolve the monomers in suitable solvent. For example, non-polar solvents used for non-polar monomers like polythene, okay, polythene, polystyrene, tetrafluoroethylene, okay. For these polymer preparations, we use non-polar solvent like benzene, toluene, like that. When you synthesize the polar polymers, you do the polar solvents. That is the key point. And same, just to heat it, but here catalyst is important, initiator is important. One advantage of this material is that for surface coating, generally people use this solution polymerization material methods, and the polymers we use this for surface coating purpose. So polyacrylonitrile, mainly polar polymers, polyacrylonitrile, polyvinyl chloride, polyacrylic acids, polyacrylamide, polyvinyl alcohol, all the polymers are prepared by PMMA, polybutadiene, by solution polymerization reactions. This is a simple photograph of the polymer preparation. Where you take a monomer, add solvent, add initiators, and keep it ready, and then starts adding the another monomer, dissolving solvents. The reaction starts. Just keep on stirring the reaction mixture. You end up with a polymer that is in the solid form that can be easily filtered it, and you can easily isolate or separate the solid polymer materials from the solution. This is a very simple method of preparing the solution polymers. Now, this important question: differentiate the addition polymerization and condensation polymerization reactions. It is a very important one. So, until now, what we discussed, if you recall it, you will get the answer. So, what are the points you will make it? Points you can have it from the examples. See here, the examples are PVC and Teflon. Here, the examples are nylon 66 and bakelite. So, how do you differentiate it? So here we need to have the monomer that has a double bond. Here we need to have a monomer that has a functional group. Here single monomer is also enough. A mixture of two or more than two monomers also is okay. Here, but compulsorily you need to have two different monomers. Here the double bond is must. Here there is a functional groups, amine, alcohol. These groups are important for the preparation of the condensation polymers. Okay, and based on the rigidity, this will be little less than the condensation polymerization. And the advantages of these materials: condensation has more advantage than the addition polymers because of the polar nature, the 3D network. Now you see the difference. Generally, addition polymers involve one monomer, whereas condensation involves two different monomers. Point number two: polymerization does not lead to loss in smaller molecules, leads to loss of small molecules. Why this loss of small molecules? Because one compound has amine group, other compound has a acid group. Definitely, one small unit will be eliminated as a byproduct when the amine and the alcohols are reacting, or when the amine and the carboxylic acid is reacting. We end up with losing a small molecule as side product. That is the point number two. So the empirical formula is the same as that of the molecular formula because only n times only we have to add. Okay, we are not going to do any changes. But here, empirical formula will change because each time you are eliminating some small group or product. So definitely there will be a change in the empirical formula. And the examples, known examples for addition polymers: PVC and Teflon. What is PVC? Polyvinyl chloride. Teflon is polytetrafluoroethylene. On the other hand, nylon 66 and bakelite are the examples for condensation polymerization reactions.